Swayam Prabha. Digital India. Educated India.
So, we will be considering 3 degree of freedom system in this present analysis. So, overall overview of the lecture is the torsional vibration of 3 disc rotor system. I will be introducing the eigenvalue problem, and basic concepts will be covered of the torsional natural frequency, mode shapes and equivalent system approach. So, this will be the overall concept which we will be introducing in the lecture. So, let us take one rotor system in which we have 3 discs. These discs are rigid, they have high polar moment of inertia. These shafts are flexible in torsion, but they do not have as such inertia effect, and here you can able to see that during torsional oscillation these discs have relative torsional twist. The first disc is having relative twist, the absolute, that is the absolute displacement phi z1, the second disc is having phi z2 and the third disc is having phi z3, and this rotor system is mounted on frictionless bearing. So, during motion as such these supports are not preventing its torsional motion. So, this particular case is also similar to the free condition. The shaft which is between disc and 1 and 2 is having torsional stiffness Kt1, and the shaft which is in between disc 2 and 3 is having stiffness Kt2. Dimensions are given here. The discs are having polar moment of inertia IP1, IP2 and IP3 of disc 1 to 3 respectively. Now, to obtain the equation of motion, we will obtain the free body diagram of each of the disc. So, this is the free body diagram of 3 discs. You can able to see that this is the free body diagram of disc 1, and in this particular case we have taken the positive convention that if we are looking from the right hand side onto the disc, the counterclockwise motion is positive direction. So, we can able to see this I have drawn in counterclockwise direction, which is the displacement of the disc, which I have taken positive in the vector form. This will be the positive direction according to the right hand rule. This is the reactive torque coming from the shaft 1. So, you can able to see this is phi z1 minus phi z2. This is the relative twist of the shaft, and this is the torsional stiffness of the shaft 1. The direction of this is opposite to the displacement. So, you can able to see this will according to the right hand rule, the vector direction will be opposite to the displacement. So, this is the free body diagram of the disc 1. We can able to take the torque balance. So, I am taking, so this is the external torque onto the disc. So, we can able to write phi z1 minus phi z2 Kt1. This is a minus sign because it is opposite to the displacement direction, should be equal to ID1 or IP1, polar moment of inertia of the disc, and the angular acceleration of the disc. So, this is the equation of motion of the first disc from the free body diagram. The second disc is connected by shaft 1 in left side and shaft 2 in the right side. So, we can able to see that The angular displacement is counterclockwise direction when we are looking the disk from the right side. So basically this is the positive direction for angular displacement. This is the torque which is coming from the shaft 1. So because this torque should be opposite to this one, because they are acting at the opposite end of the same shaft. So you can able to see the direction of this is opposite to the direction of this particular torque. And another torque from the shaft 2 is this one, in which this is the phi Z2 minus phi Z3. This is the relative twist into the torsional stiffness, and that is opposite to the displacement of the disk. So this particular torque direction I can able to show in the opposite direction to the displacement. So basically in this particular second disk we have this is one torque and this is another torque which is acting. These are external torque. So we can able to obtain the equation of motion for second disk like this. This is from this particular moment, which is in the direction of the displacement, so positive. This is negative direction. Kt2 should be equal to rotary inertia of the disk. So this is the equation of motion of the second disk. Similarly, third disk is connected in the left hand side by the shaft 2, and this particular torque will be equal and opposite to this one. So the torque direction will be opposite to the previous one. Sorry, this will be opposite to this one, which is left side. Now it is right side, and this we are taking in the positive direction, angular displacement direction. So from here we can able to obtain the equation of motion for the third disk, that is phi Z2 minus phi Z3. Kt2 should be equal to inertia of the third disk. So you can able to see that we obtain equation of motion of all three disks, and we can able to rearrange these in matrix form. That will be more convenient to handle. So in the next slide, so this is the equation of motion which we derived in the previous slide. I have put them in a matrix form. So you can able to see this. This is nothing but the mass matrix of the rotor system. This is the inertias. This is angular accelerations. These are the displacements, and all the stiffness terms are here. This stiffness matrix, you can able to see this is a symmetric matrix. In this particular case, the mass matrix is diagonal, and the form of this equation is similar to a standard form of the multi-degree of freedom system, vibration system. So where you can see M is here this matrix, this vector is this vector, stiffness matrix is this one, and this is the displacement vector. Now for free vibration, because we are dealing with the free vibration, we expect the displacement will be having some amplitude, and harmonic component, that will be the natural frequency of the system. So if we substitute this in the equation of motion, this one, you can able to see that we need to derive or take derivative of this with respect to x, with respect to t, and because this is a constant, so we will get omega square for that particular case. So if we substitute, I can derivate this twice. So, basically I will be getting this expression, and this expression, if we substitute these two in the equation of motion, I can get this equation, in which now you can able to see omega square minus has come here, and I have taken the displacement vector, which is amplitudes, this capital X outside. So, now you can able to see this is a homogeneous equation, and the one solution is that all the displacements are 0. So, in that particular case motion is not taking place. So, we are not interested in such analysis. So, if for non-zero value of this displacement, the determinant of this should be 0. So, that will give a polynomial. So, you can able to see that if we take the determinant of those matrices to 0, so that is something. So, this is nothing but m plus k minus omega n f square, determinant equal to 0. So, we will get a polynomial like this. So, we can able to see that the one solution of this is when this natural frequency itself is equal to 0, and second is when these terms are 0. So, from first one we got 0 natural frequency, second term we will be getting 2 more roots, positive roots. So, that expression expanded here. So, if we know the polar moment of inertia of various disks, the torsional stiffness of the shafts, we can able to obtain the natural frequency of the system. So, here we got 3 natural frequency, out of that one is having 0 value. So, we have seen how to obtain the natural frequency of a 3 disk rotor system. Now, when we are having multi degree of freedom system, then we need to obtain the relative twist or relative angular displacement of the disk, that means the mode shape of the disk. So, now we will see how we can able to obtain the mode shape from the our equation of motions. So, for that we will take this particular equation. So, in this equation we can able to expand any two of the equations. So, like first equation and second equation we can take, and in the subsequent slide we have. So, this is the first equation from that equation, and from this you can able to see that we can able to obtain the ratio between the two displacements, angular displacements, like displacement of the disk 2 divided by displacement of disk 1, that will be in terms of various stiffness, mass moment of inertia and the natural frequency of the system. Similarly, from the second equation of that matrix equation, we will get these expression, and from here you can able to see that we can able to obtain the ratio of the displacement 3 with respect to 1. This particular displacement can be eliminated from the here. So, because we have already relationship between the 2 and 1, so that can be eliminated here. So, the ratio of the displacement of 3 with respect to 1, this expression we obtained. After simplification, this will be of this form. You can able to see this also contains various polar moment of inertia, torsional stiffness of the shaft and natural frequency. So, these two equations, this equation and this equation, can be used to obtain the relative twist between disk 2 and 1 and 3 and 1 for corresponding to various natural frequency. So, like first one was the 0 natural frequency. So, we need to substitute 0 here. So, you can able to see that the repeating the last sentence. So, these two equations can be used to obtain the relative displacements, and for various natural frequency, like for first natural frequency which is having 0 value, we can able to substitute omega NF as 0. So, that will be the relative twist between two disk 2 and 1. Similarly, for 0 natural frequency, this term and this term will vanish. So, the remaining term will give us the relative displacement between the disk 3 and 1. The same exercise we can able to do for the second natural frequency, that is a non-zero value. So, if you substitute that here, we will get the relative displacements corresponding to the second natural frequency. Here, for corresponding to the second natural frequency, we will get the relative twist between disk 3 and 1. And last, because we have the 3 natural frequency, so if we put the third natural frequency corresponding to that natural frequency, we will be getting the relative twist between disk 2 and 1 from here and 3 and 1 from this expression. So, these two can be used for obtaining the relative twist between various disks corresponding to different natural frequencies. Now, through a simple example, we will see how we can able to get the natural frequency and mode shape for 3 disk rotor system. So, here we have turbine, coupling, generator system, and as such these bearings are frictionless, and as such they are not imparting any role in the torsional vibration of this system. So, basically we want to obtain the torsional natural frequency of the system. Various geometries are given. So, L1, L2 are nothing but the distance between the turbine and coupling, and coupling to generator. So, these are 1 meter. Various property of the shafts are given, like 0.2 is the diameter, 0.2 meter is the diameter of the shaft, and we have torsional stiffness of the shaft in this particular region, because you can able to see that as such we are not considering the mass of the shaft. So, this segment and this segment of the shaft will not play any role in the torsional oscillation, only these two will be playing role, because there is no mass attached at these ends. So, the torsional stiffness of this segment and this segments are same, because the dimensions are same, and it is given here. Now, these expressions which we know for natural frequency of the system, so we can able to substitute, and here we can able to get first as 0 natural frequency and 2 flexible mode natural frequencies 611.56 radians per second and 2325.55 radians per second. Now, corresponding to this, if we want to obtain the natural mode shapes, we can able to use these expressions, and this ratio which we obtained earlier is of this form. And in this particular case, you can see when the natural frequency is 0, both the disk 2 and 3 relative to disk 1 is having same motion. That is something like all the disks are having same amount of displacement. So, there will not be any relative twist between them. So, that we call it as a rigid body mode. Corresponding to the second natural frequency, if we substitute the values in these two expressions, we will get this ratio. So, you can able to see that one is positive, another is negative. And if we want to plot these relative displacements, we can able to plot it. So, this is the plot of the mode shape. The first one was having all disks same displacement. So, this is a turbine, coupling and generator. These are the displacement, 3 displacements. For the second natural frequency, you can able to see that this is for turbine. We can take this as 1. Corresponding to that, second disk will be having 0.26 displacement, and the third will be having negative. So, shown in the negative direction. Corresponding to the third natural frequency, here if we substitute this in these two ratios, we will see that one becomes negative and another is positive. So, the mode shape will take this shape. the disk 1, if we take value 1, the disk 2 will be having a large negative value and disk 3 will be having small positive value. So, here you can able to see that in second natural frequency there are two nodes appearing where there will not be any torsional oscillation. In this first natural frequency there will be one node between coupling and the generator, and these nodes are very important because high level of stresses we expect at these nodes. Now, the same problem will solve using a indirect approach. In this particular approach we will not be obtaining the equation of motion from free body diagram, but we will try to obtain the natural frequency of the system by qualitative nature of the mode shapes of the system. So, in this, because we know there are 3 disks and there are 3 possible modes, and those 3 possible modes, from that we will try to obtain the natural frequency of the system. So, let us see how this can be obtained. So, this is the 3 rotor system. We are interested in obtaining the torsional vibration of torsional natural frequency of this, because the supports are something like free corresponding to the torsional vibration. So, in this particular case we expect that the one natural frequency will be 0, because it is very clear that when we have free vibration condition, boundary conditions, we have one of the natural frequency 0, and correspondingly the mode shapes is we call it a rigid body mode, in which all the disks are having same displacement. So, as such this particular mode is having no practical relevance, so we will not be considering that particular natural frequency determination, but we are interested in obtaining the 2 other natural frequency which are corresponding to flexible mode. So, for this flexible mode you can able to see we can have this is the possible mode shape, in which you can able to see that this is the one of the mode shape, in which these 2 disks are having displacement in synchronous with each other, but this particular disk is having displacement in the anti-synchronous with this. So, that means in one of the mode we expect that maybe this and this disk will be having same direction of motion, let us say clockwise, and this will be having displacement in the other direction and anti-clockwise. So, this has been shown here. So, you can see this is the 0 axis, and we have positive direction displacement of these 2 disks, but this third disk is having negative direction. So, this is one of the possible natural mode this particular disk rotor system can have. Other possibility is maybe the outer 2 disks are having same direction of motion, maybe clockwise or anti-clockwise, but the central one is having motion opposite to the other 2. So, here you can able to see that this is having positive displacement, this is also having positive displacement, but the middle one is having opposite to these 2. So, this is another possible mode. In this second case, we have taken this 2 is having same displacement. It may happen that maybe the second and third disk is having same displacement as compared to the first one. So, other case is possible, but that will be determined by the relative mass moment of inertia of the disk as well as the stiffness. So, in this particular case we assume a specific case, and depending upon the relative values of the natural frequency and the torsional stiffness of the shaft, we can have a other possible mode shape in which the disk 2 and 3 is having same displacement as compared to the 1. But for the present case, let us consider that disk 1 and 2 are having same displacement as compared to the third one. So, now if we consider this particular system, let us say the third one case in which we have the two outer discs having positive displacement and the central disc is having negative displacement. So, this is disc 1 location, this is disc 2 location, and this is 3 disc location. So, in this particular case you can able to see these are the node position where there is no displacement. So, as such we had the rotor system like this. Okay, this mounted on frictionless bearing. So, you can able to see that node position is here and here. So, we can able to break a 3 rotor system into 3 single rotor system like this. So, I am taking one of the rotor system from the node position as this one. So, this particular rotor system I am taking as separately. Similarly, here because this is a node position, so 0 displacement. So, this rotor system is another I am taking separately, and in between these two I am taking a third system like this. So, you can able to see that we had 3 disc rotor system earlier. This was single system. Based on the information of the mode shape, we have broken this single system to 3 systems, 1, 2, 3. This is a cantilever kind of boundary condition. This is also cantilever kind of boundary condition. This we know is IP3, this is IP1, this is having IP2 moment of inertia, and these lengths, if we know at present they are unknown, the node position is unknown. So, if we know that, we can able to obtain the natural frequency of this system, and this system, and because we have broken them from a original system, natural frequency of all these 3 systems should be same and should be equal to the original system. So, this is the basic idea by which we can able to obtain the natural frequency of the original system. So, here the main aim is to obtain what are these segments, these lengths of the shaft segment. If we can obtain this line segment length, then we can able to obtain the natural frequency of either of these natural system, which and all are belonging to the same system. So, their natural frequency should be same as the original system. So, now we will be writing the natural frequency of these systems for unknown length of the shafts, and from there we will try to obtain the length of these shaft segment. So, this is the natural frequency of the cantilever first one, which is left side of the figure. So, this is the IP1, and this is the torsional stiffness of the shaft segment of the cantilever thing, and in this this length is unknown. This L1 is unknown to us, but other properties we know. So, this is the natural frequency expression for the left hand side cantilever beam rotor system, single disc rotor system. This is for the right side, the extreme right side corresponding to the disc 3. So, IP3, and you can able to see this particular length is the shaft segment for the that particular cantilever beam in the right side. This is also unknown. Then the third natural frequency, that is for the middle rotor system, which was having boundary condition of fixed condition and the disc in between, and if we don't have the idea about the length, because these lengths are unknown. So, This natural frequency we are writing as the torsional stiffness of the shaft and the polar moment of inertia of the disc 2. So, for fixed case, this torsional stiffness of the shaft in terms of unknown lengths we can able to obtain like this. We can able to see that L1 is the total length of the left hand side of the shaft segment. L1 is from here to here, and this is L3. And if you know this, we can able to get this by subtracting L1 minus this length. So, the same thing we are done here. So, this is the torsional stiffness of the shaft, and this we can able to substitute here to get the natural frequency. So, here you can able to see that L1 subscript 2, L3 subscript 2 is unknown, and basically if you see overall we have one is this equation, this is second equation, and this is the third equation. So, we have three equations. They are natural frequency expression and they belong to the same natural frequency. So, that means we can able to equate the equation 1 and 2. If we equate these two, you can able to see that we will get this relationship between the L1 subscript 2 and L3 subscript 2. So, these are the shaft segment lengths. So, this is L1 subscript 2 and this is L3 subscript 2. So, we got one relationship between them. Then if we equate the first one and the third one, we will get this expression. So, this is another expression which is relating the L1 subscript 2 and L3 subscript 2, and using this, in this equation we can able to eliminate one of the unknown, that is L1 subscript 2. So, we can able to see we can able to substitute here in other places. So, we will left with only the L3 subscript 2 in this expression. So, if we do that, we will get. So, this is the summary of. So, from first two equation we got this relation, from first and 3 we got their relation, and if we eliminate L1 subscript 2 from this, using this we will get a polynomial in terms of the L3 subscript 2. So, we can able to see that we can able to solve this polynomial for this segment, and if we get this segment L3 subscript 2, using this we can able to get this also. And once we know these two value, we can come back to the figure. We can able to see that if you know this and this, we can able to get this expression, this shaft length and this shaft length. So, we will be basically we have obtained the node positions now, and using these we can able to get the natural frequency of the system. So, any of these we can able to use it to obtain the natural frequency. All these will give the same natural frequency. Now, through one simple example, we will try to see this 3 disc rotor system, how it can be analyzed. So, we are interested in the torsional natural frequency of a turbine coupling generator rotor system. This is shown here. This is a turbine, this is a coupling generator. As such, is having free bond support. So, as such, they are not imparting any torsional vibration or torsional torque, external torque to the rotor system. And various property of the 3 major mass of the turbine and the coupling and the generator is given here. The shaft property is also given here. We are assuming that the shaft is uniform, and as such they don't have inertia, and bearing is having no frictional torque onto the rotor. And the length of this particular shaft segment between the turbine and the coupling, and between coupling and the generator, is 1 meter. And as such, for the method, indirect method, which we have studied, in which from the possible flexible modes of the system, directly we try to obtain the node location, and from node location we could able to obtain the natural frequency of the system. So let us see through one example how it can be done. The example is the same as we have done previously. So for this particular thing, we have seen that we get a polynomial using the indirect method like this, and if we substitute various values of the polar moment of inertia, and in this expression we will see that this polynomial will be reduced to this expression, and here from here we will get two roots, because this is a quadratic in L3 2. We will get two roots, and corresponding to these two roots, using this expression we will get two possible values of the L1 subscript 2. So we can able to see that we have two combinations of the L1 subscript 2, L3 subscript 2. This is one possible combination, and this is another possible combination. So now let us try to see what are these values they represent in the rotor system. So for first case, that is first possible values, L1 is this one, and L3 subscript 2 is this one. So basically these are the these distances, this one and this one. So you can able to see that if node is here and node is here, this system can be broken into 3 single rotor system. And now because we know the length of this, so natural frequency of this can be obtained, or natural frequency of this can be obtained, even this can be obtained, and they should be same as the natural frequency of this system. Similarly, for the second combination of the L1 subscript 2 and L3 subscript 2, we have these values. For this particular case, you can see that this is the node position. In this particular case, there are two possible, so 1.3446. So that is, if we take 1.3446, it will, so this is one of the system, and other end this is 0.6723 from the right side. So this is another node. So from this we get this particular single system, single degree of freedom. We can able to see that from 1.3446, basically we are getting a node away from this here. So that is not possible that we have two nodes in between the two shafts or two discs, because we are not considering the shaft mass. So this particular combination, in which this is feasible one, because we can have a node here, but another 1.3446 is coming here only. So it is not possible that we can have two nodes in between these two discs, because we are not considering the inertia of the shaft. So this is having no relevance, only this is possible. So if we take that, so that is, this will be a cantilever beam of this, and we can able to obtain the natural frequency of this corresponding to this length. That will give us the second natural frequency. So basically from the same solution we are getting both the flexible natural frequency, one is from this and another from this, or even we can able to, if we know the natural frequency expression for this 2 degree of freedom system, this will also be having same natural frequency as this one or this one for the second mode, in which only single node is possible. So let us obtain. So this is one of the natural frequency corresponding to 2 nodes, and this is corresponding to 1 node. So you can able to see that we could able to obtain not only the 2 node natural frequency as well as the 1 node natural frequency from the 2 possible values of the lengths which we obtained from the quadratic equation. In the previous lecture we discussed about the stepped shaft. Now through one numerical example, let us see how that particular rotor system in which stepped shafts are there, natural frequency can be obtained. So in this particular case, we have considered a stepped shaft like this, where its dimensions are shown here, length and diameter. We are not considering the such inertia of the shaft, only discs are having inertia, and all the dimensions and parameters are given in this. Now our aim is to obtain the natural frequency of this 2 rotor system. So various geometrical parameter from the geometry of the shaft can be obtained. Torsion of the first shaft segment, second shaft segment, third shaft segment, because they have different steps, so they can be obtained. So once we have these, we can able to obtain the equivalent length of the shaft corresponding to one of the shaft diameter, which we have taken as the third one. So corresponding to this, this is the equivalent length of the shaft. Now we can able to obtain the equivalent stiffness corresponding to the uniform shaft having a diameter same as the third shaft step. So this is the equivalent stiffness of that, and we can able to obtain the natural frequency, especially the flexible one, because the first is 0, we are not interested in that, we are interested in the flexible natural frequency. So that is flexible mode natural frequency. So this is given by this expression, in which this is the equivalent stiffness of the uniform shaft. So this is the natural frequency of the system. So once we obtain this, the now aim is to have the node location. Where is the node? So for that we know that the relative amplitude is given by this expression. So this is the ratio of the 2 amplitudes. The node location ratio is given by this expression, and we know that total length of the either side of the node in the uniform shaft is having value equal to the equivalent length. So from these 2 expression we can able to obtain the node location. And so if we see in the figure, this is the equivalent uniform shaft, and we have a node location here. Okay. Now we have located the node also. So this length we know. So we know the node location, which is for this particular problem coming into the second step position. And now corresponding to this, actually this is corresponding to the second shaft step, and node is here. So from, let us say, this end, the position of the node is AE, and from this is BE. So this ratio, as we have seen in the analysis, now we know this ratio. In original system, the node location will be in proportional to this equivalent shaft system. So from here you can able to see that this ratio is this one, and total length of the original step shaft of the second shaft step is 0.3. So from this we can able to get the A and B, and using these two expression we can able to obtain what is the actual position of the node in the step shaft. So in the present lecture we mainly analyze 3 rotor system. We consider 2 approaches. One, by obtaining the equation of motion, we obtain the natural frequency and mode shape of the system, and by indirect approach, in which we use the mode shape information and we try to obtain the node position, and from there we obtain the natural frequency of the system. We solved couple of numerical example so that the method is more clear, and not only for the 3-disk system, also for 2-disk system, which we covered in the previous lecture, that also we have seen through the numerical example. Now, as the number of degree of freedom or the number of disks in the rotor system will be increasing, we will face difficulty in solving the bigger polynomial as a frequency equation, or so here we feel that there is a need for a more systematic approach, by which even if we are handling a bigger system, we should able to solve using less difficulty. So in the next lecture we will see more systematic approach. There is a transfer matrix method, which is quite popular in torsional vibration of rotor system, especially when we have bigger systems.